Welcome everyone to Geol 105 Environmental Geology. This is Dr. Widanagamage. My office is located 118D Carrier Hall in School of Engineering. The textbook for the course is Introduction to Environmental Geology by Edward Keller. 5th edition is recommended. As you all know, this course is web course and Blackboard enabled. So weekly materials will be uploaded to Blackboard. You can expect one chapter or two chapters every week depending on the weight of the materials. Each lecture or chapter will have practice questions, quiz, or both by the end of the week. You can expect very similar type of questions in your exams. Quizzes and or assignments are expected to complete and submit through Blackboard following instructions. Office hours are online, that means you can expect email responses from me during that time, Monday, Wednesday, Friday, 2 to 3 p.m. Please make sure to write your name, student ID, course number in subject line of your email. Why do we study environmental geology? We live here. We live in the environment. When you think about geology, it is the science of processes related to composition, structure, and history of Earth and its life. When it comes to environmental geology, it is more applied geology. Especially, it is the use of geological information to help us solve conflicts in land use, to minimize environmental degradation, and maximize the beneficial results of using our natural and modified environments. In this course, you will be learning about natural resources, geological hazards, environmental protection. All manufactured objects depending on Earth's resources. Most resources are limited in quantity and they are non-renewable. For example, many of today's medications are derived from benzene, and benzene in turn is derived from petroleum. Almost all over-the-counter pain medications such as aspirin are based on these petrochemicals. Mining, metals, industrial minerals, gems, these are major economically important mining materials. Inappropriate mining can release acid waste into groundwater, causing environmental issues. Petroleum exfoliations, similarly, removal, transportation, and waste disposal can damage the environment. So in this slide, you can see a picture of acid mine drainage, the right hand side. You can see very brownish, yellowish water transporting through this river. So acid mine drainage or acid rock drainage refers to the runoff formed of acidic water and frequently comes from areas where metal mines or coal mines in practice. This is a very large environmental issue. We'll be talking about earthquakes, landslides, volcanic eruptions, floods when we talk about geological hazards in this course. Water, soil, air. The protection of these three components is considered as the major environmental protection. Look at this picture. Look for the contamination in here. Mixing of gasoline with toxic chemicals. To understand this kind of process and to identify this kind of problem, you will need the knowledge of environmental geology. For example, you should know what is the permeability of the rocks surrounding, what is the porosity of the rocks and soil surrounding, and how this contaminant going to move to your drinking water or to the groundwater. These things needs to be understood very carefully and correctly. Then you will need the knowledge of environmental geology in order to understand these kind of conditions. Let's briefly look at solar system. I'm pretty sure you have learned about solar system before in your high school earth science class or maybe any other geology class if you have taken any. Anyway, solar system is based on nebula theory and protoplanet hypothesis. The Eagle Nebula, with its intensely cold gas and dust, finger-like pillars where new stars are thought to be forming. The solar system formed around 4.5 billion years ago from a huge swirling cloud of dust. You can see these pictures and figures and see how our planetary system has been formed. How do we know this? We know this because advances in technology, such as Hubble telescope, have allowed us to look deep into space to observe the birth of stars similar to our sun. Based on this information, we do have terrestrial planets versus Jovian planets. I'm not going into explain too much on this because this is not the major focus of the course. So I will let you read these 2 slides and let me know if you do have any questions. Alright, so now let's look at the differentiation of Earth. Primitive Earth, the first Earth, did not have any layers, but now we do. So what are these layers? Based on chemical properties, we do have 3 different layers mainly: crust, mantle, core. Core can be subdivided into outer core and inner core. This is based on chemical properties, based on chemistry. For example, crust will have a lot of oxygen and silicon. Mantle rocks will have a lot of iron and magnesium. Core, the outer core, is liquid, mostly iron. Inner core, it's a solid, is mostly iron and nickel. Based on physical or mechanical properties, Earth can subdivide it into a couple of layers, mainly lithosphere, asthenosphere, mesosphere, outer core, inner core. What is lithosphere? This is the rigid, brittle outer shell of the Earth. This will be known as the lithospheric slabs in plate tectonics. These are the plates that you will learn in plate tectonics class. The lithosphere composed of both crust and the upper part of the mantle. Asthenosphere is plastic, very weak, it's ductile. It's a very weak zone on which the lithospheric slabs are moving in plate tectonics. Isostasy is another important concept to understand what this means. This refers to the state of gravitational equilibrium between Earth's lithosphere and asthenosphere, such that the tectonic plates at an elevation which depending on thickness and density. So the tectonic plates moving on top of the asthenosphere based on this principle. What drives plate tectonics? And what are the plate boundaries? The theory of plate tectonics originally proposed in 1960 by Alfred Wegener. Initially, it was known as continental drifting. After certain years, it was known as plate tectonic theory. This included new understanding of the seafloor and explanation of driving force. This describes lithosphere as being broken into plates that are in motion. This explains origin and distribution of volcanoes, earthquakes, fault zones, and mountain belts, which we will be learning in future slides. The driving force for plate tectonics is thermal convection, circulation of thermal currents. As you can see, warm currents rise up, cold currents sinks down. The warm currents represented by the red arrows, cold currents represented by these blue arrows. The warm currents rise up because of the less density, cold currents sinking down because of high density. Thermal convection, when it comes to plate tectonics, you can see the red arrow rising up because of less density. The cold arrows or the blue color arrows represent the sinking of the lithospheric slabs. There are 3 major plate boundaries that we will be learning in this class: divergent, convergent, and transform boundaries. Divergent boundaries, plates move apart from each other and magma rises from the bottom, cools and forms new lithosphere. You can see the creation of crust at divergent boundaries. For the same reason, these boundaries are known as constructive type of plate boundaries. This is typically expressed as mid-oceanic ridges, example mid-Atlantic ridge, where you can see the Atlantic Ocean expanding because of this divergent plate boundary. Convergent boundaries. Plates move towards each other. There are different categories of convergent boundaries where you will expect to see oceanic convergence, oceanic continental convergence, or continental convergence. In this diagram, you're looking at oceanic continental convergence. Oceanic crust or oceanic lithosphere is sinking underneath the continental lithosphere because oceanic crust or oceanic lithosphere is higher in density compared to the continental crust. Oceanic plates may sink into mantle along subduction zone marked by deep oceanic trench. Transformed boundary. This is the third and the last type of plate boundary. Plates slide past one another. There is no construction or destruction of the crust during transformed plate boundaries. Fault zones, earthquakes mark boundary. You can expect to see lots and lots of earthquakes at this type of plate boundary. San Andreas Fault in California is an example for transform fault or the transform plate boundary.